So let's look at suddenly applied load. So in suddenly applied load, we are going to see unit step function. So this is unit step function or Heaviside step function. Heaviside step function. So which is unit u of t minus j will be given as like this. So where this is t, this is the function u of t, and this is the point equal to a. So in this case, when t is equal to less than t is equal to less than a, it becomes 0. T is equal to greater than a, it is 1. T equal to a, it is 1 by 2. So this is the definition of Heaviside step function. So what is suddenly applied load? Suddenly applied load is, so we are applying the load like this, load of f naught with this unit step function. So this becomes f naught when t less than a, f naught by 2 is t equal to a, f naught, sorry, this is 0 before applying. So we are applying the load at t is equal to a. So this is t greater than a. So this is a, this is t, this is f naught, e of t. So now we use this in terms of vibrations. So for that we have governing equation with the forcing f naught u of t minus k. So with boundary condition. So now we need to solve this. So I have told this is non-homogeneous equation, though therefore we have to find complementary function, then particular integral. For this complementary function will be e power minus neta omega t a cos omega dt plus b sine omega dt. So this is coming from the characteristic equation. So minus b minus c divided by 2m, c divided by 2m plus or minus root of c square minus 4km, so divided by 2m. So this is the root. So now from this we will get this equation. So let's go to pi. How to find this pi? Mx double dot plus cx dot plus kx equal to f naught u of t minus a. So before when t is equal to t less than a, it is a homogeneous equation. So for that we have the solution here. So when t is equal to greater than a, then this equation becomes mx double dot plus f naught. So now this is we need to solve this differential equations. So differential equation have the property, so the solution will have the same form of the forcing. So since the forcing is constant, the assumed solution will be constant alpha. So now I substitute this thing into the equation here. So I will get mx double dot, x dot is 0, x double dot equal to 0, therefore is 0 x double dot plus 0 c m0 c0. So k alpha equal to f naught, therefore alpha is equal to f naught divided by k. So is the solution. So therefore x of t will be e power minus neta omega t a cos omega dt plus b sine omega dt, this is the solution of homogeneous part, plus f naught by k is the solution of particular integral of non-homogeneous part. So this is the final equation we have. Now we apply boundary condition, get the equation x naught x dot of 0 equal to x naught dot. So now I need to find x of t. So e power minus neta omega t minus a omega d sine omega dt plus b omega d cos omega dt plus 0 not 0, so uv rule, no, so plus, so this is minus neta will come front, so minus neta omega a cos omega dt plus b sine omega dt, so e power minus neta omega t plus derivative of this part is 0, the second part is 0. So now we substitute the condition x of 0 equal to x naught equal to a, so b becomes 0, f naught by k, so therefore a equal to x naught minus f naught by k. X dot of 0 will be x dot naught equal to b omega d minus neta omega a, yeah, right. So now we substitute a here, p omega d minus neta omega a equal to x naught by f naught divided by k, so therefore we will write b omega d minus neta omega x naught plus neta omega f naught by k x naught dot, so therefore b equal to x naught plus neta omega x naught minus neta omega f naught by k divided by omega d x naught, so we don't need to, so we are not supposed to expand this, so I will write this in this compact form. So this is a and this is b, so we will substitute into the solution, so x of t will be e power minus neta omega t, so a is x naught minus f naught by k a cos omega dt plus b is x naught plus neta omega x naught minus f naught by k omega d sine omega dt plus f naught by k. So now, so now we applying the data of boundary condition, x of 0 will be 0, x naught equal to 0, so this makes this equation e power minus neta omega t, so this becomes minus f naught by k cos omega dt plus x naught is 0 neta omega minus f naught by k divided by omega d sine omega dt f naught by k, so this will be, so minus f naught by k cos omega dt cos, so this omega d can be written in terms of omega 1 minus neta square, so omega will get cancelled, Now we will have this formula. So minus f naught by k neta by 1 minus neta square sine of omega dt plus f naught by k. So we will take this f naught common, f naught by k common. So which will, so we will take minus f naught by common. No, we will take f naught by common. Neta omega t minus cos omega dt. We will take this minus also, plus neta by 1 minus neta square root of sine omega dt plus 1. This is, so this will be simply written like this. So this is the response of the system to the unit load with the boundary condition x of 0 equal to 0, x dot of 0 equal to 0. Let's look at remarks of this response. The first one is when the damping is 0, then the response will be, so you put f naught by k and 1 minus exponential becomes 0 cos of omega dt sine this neta goes to 0, so therefore this is the equation. So now we plot this curve. So this is, and this value will vary. So when cos omega t equal to 0, this is 1. So cos omega d2 goes, this will goes from minus 1 to plus 1. This is plus 1. So therefore the equation this will go to 0 to 2, right? Yeah. So then we need to draw here one, the another one is here. So this is f naught by 2 f naught by k, this is f naught by k, and k t is starting from the 0, so therefore it will goes like this. So this point, so here if you consider this to this, the amplitude of this vibration is 2k. So this is the first observation, which is a suddenly applied load. The maximum displacement x of t is twice of the f naught by k. So this is in when there is a gradually forced damping, and this is suddenly applied unit force damping. The difference is in gradually applied load, x of t will be f naught by k only. So this is gradually applied load. So this is unit suddenly applied, so with unit step function load. So for this the maximum of t is 2 f naught by k. So this is the one important result. So then we include the damping. So damping is not 0, so that means it cannot be negative, so it will be positive. So when it is not equal to 0, so then the response graph will be, so this is f naught by k, this is 2 f naught by k. So this is the line f naught by k. So what happens, we will get a profile like this. So here also we will get a profile. So So then the response will be like this. So it will gradually comes to the value where it is since it is a unit step load, it will decay to 0, so decay to f naught by k. So here you need to know this x max. So here this x max will be little less than 2 f naught by k. Here it will start with f naught by k, it gradually decreases and it decreases to 0. So it decreases to f naught by k, which is the static deflection. The third remark will be what is unit step step function, how to produce this in experimental way. So we have, so this is the time, sorry, so this is the graph of t. So I am producing, so it is impossible to produce the wave very sharply, so therefore it will suddenly gradually increase and it will stay. So there will be always some time, so this we call it tc. So tc, this is time needed to apply the load, apply the load. So so this one is equivalent to the step function. So like this, when, so this will be equivalent to this when this tc is much less than time period, which is 2 pi by omega. So omega is the natural frequency. So if this natural frequency of the system, if this condition is satisfied, then we can call this loading that we are giving as a unit step function. Finally, so we have the equation, so x of t of f naught by k 1 minus e power minus eta omega t a of cos omega dt plus b sin omega dt. So this is, so yeah, this is the equation we had. So this mx double dot plus cx dot plus kx equal to, so what is the equation, f naught u of t minus a with the boundary condition x of 0, x dot of 0 equal to 0. So for this solution, for this equation, so above is the solution. So here when this f naught equal to 1, so when this f naught equal to 1, so therefore this equation turns into like this, equal to f equal to u of t minus a. So this is called unit step function, unit step function forcing. So corresponding x of t is 1 by k 1 minus e power minus eta omega t this is called unit step response. So this one we need to memorize it. So this is the one important formula that we will use it again in the next lecture. So there is a slight correction. So this is not a and b. So this is 1, this is eta by 1 minus eta square root. Here eta by 1 minus eta square root. So now you can finish this. So now it is correct.